Okay, please take a look on your quiz 6, 7, 8. Quiz 3, 4, 5 will do this weekend. Supposed to be on Saturday evening. I make it Sunday evening to give you one extra day to work on that. Okay, Thomas, what happened if I don't have printer? Then just write it down. Thomas, what happened if I get sick? Then you do 2 problems a day instead of all at once, but you still need to do something. Thomas, I don't want to get sick. Nobody wants to get sick, I understand. But still, if anybody responsible of you being sick, it's you, not me. Okay? Because I get this email, somebody says, Thomas, I get sick in the last 5 days, and then can you give me some extra time to do that, right? Now the thing is, like, I get that request today or yesterday, I don't remember, and the quiz is actually due last Saturday, right? Okay, and I post that quiz 1, 2, actually at the beginning or the middle of the second week. So you have at least 10 days to work on that quiz 1, 2. Okay. The fact that that person chose not to do it early enough means that person was willing to accept the consequence if he or she didn't have enough time to do it last minute for any reason. Okay, so it's not that I am being an, what you want to call it. It's not that I'm being an ass. No, but your argument that you were sick, therefore you don't have enough time to do that, implies that you have been sick for too long. But according to that person said, Thomas, I was sick in the last 5 days. The last 5 days, even if I count from yesterday, means the time you get sick was actually last week, Thursday. But I post that actually on Wednesday, the week before that. Okay, so when you can do it, you have time to do it. You don't do it. When you don't have time to do it, then you just blame it on being sick. No, I don't play that kind of game. Okay, I don't play that kind of game. Now, at least the person, one of them actually talk to me and say, Thomas, then I try to understand, and in future it won't happen anymore. Okay, good. At least you try to see from my point of view. The thing, my point is this: it's different from a test. Okay, it's not like a test. The test is we decide. For example, your test 1 will be which day? Your test 1 will be two weeks from now, as I remember. So your test 1 will be on the 17th, right? Okay. Now, what happened if on that day you happen to be sick? Then I give you a makeup test, right? Which is that Saturday. Remember? Okay. But our quiz is different. It's not that I post it right now. You need to turn it in right now. No. Okay. Your test your quiz 1, 2 due on the 27th. But when I post it around, I think around the 17th. I posted around on the 17th. And even when I post it, you can start working on that already. Okay, that's why it's like if you wait until last minute to do it and then you happen to be sick and you use that as an excuse not to turn it in on time, I cannot accept that though, because you purposely not doing it early enough, right? And then just quote unquote blame it on COVID. No, it doesn't work that way. Okay, it doesn't work that way. You know, it doesn't work that way. Now, at the same time, the reason I insist to have this is because to run it this way, because I want you to develop that sense of kind of like, if you can do it now, do it now. Do not procrastinate. And when you procrastinate, there is a consequence that come to that. And do not, how to say, you cannot choose to do one thing without willingness to accept the consequence of that choice. Okay, please understand that though. Please understand that though. Okay, it's not that we have only that 2 hours that you need to take the test and you happen to be sick and I become such a not understanding person. I don't give you makeup test. No, it's not that case. The quiz is given a lot earlier such that you basically can start working on that with plenty of time. Okay, even if with that plenty of time you still don't have enough time, then something really wrong with your time management. Okay, well anyway, let me come back here. I don't think I see anything wrong with quiz 3, 4, 5, which is due this Sunday. But if I were you, I will do it right away. There are 3 pages. I give you a lot of spaces though, so I hope you don't get scared with that 3 pages. Now the thing is, when I look at this quiz 6, 8, when I look at this quiz 6, 7, 8, on my file, this is what it looks like, and this is what it's supposed to look like. But when I look at my Canvas preview, it looks quite funny. Like it suddenly come up with this kind of strange notation. Let me enlarge that so that you can see that better. It looks like that. Okay. Now, Jonathan helped me earlier and he said, Thomas, I downloaded and it looks okay. Now, I want to make sure that all of you have the same case. What I don't want to happen is like last minute, you said, oh, Thomas, you know, when I print it out, it looks funny. It's like, why don't you tell me earlier when I asked you to do it? Okay. So please do that at least by the end of today. If it happens to look funny on your when you print it out, then I would try to find a way to have you so that you can have the proper one. Yeah, it's corrupted in the preview, but it's downloaded should be fine. That's what. So somebody told me that our Canvas preview could not handle the new software from Microsoft Office when it comes to the math editor. Yeah, that's what somebody told me. That's why that when they try to use a math type called a LaTeX, it's corrupted also. You know, at least on the view. But when we print it out, it's still okay. Now, the good thing is that I use PDF files so that it should be uniform to everybody. Okay, so for now, I don't see any issue with this, right? Okay, let me start with going back to our 7.1. I'm recording this. Yeah. 7.1b. Is there any problem from this 7.1 you want me to go over? Beside the one I already went over, is there anything else you want me to go over? Something that when you see that, oh, Thomas, this looks scary. Can you go over that?
Thomas,
Sorry.
sorry.
Okay, either one of you.
Okay. I just wanted to ask, because I've been redoing the homework. Is there any chance you could do a problem from 6.4?
I can.
Number 31.
6.4, number 31.
Mm-hmm.
Section 6.4, number 31. Differentiate the function. Differentiate. Here we have fx equals to x over 1 minus natural log of x minus 1. And find the domain. Of fx. Okay, differentiation first. So the derivative will be, I need to apply quotient rule. The bottom looks like this. Let me just leave it like that. On the top, that will be the derivative of x times 1 minus ln x minus 1. I don't write down the derivative of x because it's just 1, right? And then minus x times the derivative of that ugly guy, that will be 1 over x minus 1 with negative. Okay, so we have 1 minus natural log of x minus 1 plus x over x minus 1. Big over 1 minus natural log of x minus 1 is quantity squared. I will get rid of the complex fraction. I multiply by the LCD over the LCD. That will give me x minus 1 minus x minus 1 times natural log of x minus 1 plus x over x minus 1 times 1 minus natural log of x minus 1 quantity squared. Last step, I think on the top we can combine like terms, right, on the top. So I'll get 2x minus 1 minus x times 1 natural log of x minus 1 over x minus 1 times this. I wonder if I can simplify any further, but I don't think so. I don't think so. That's the simplest I see. Okay, that's for the derivative. Now, how about the domain of that function? The domain of that function, there are two parts. First, that x minus 1 has to be non-negative, right? Because that's the argument of the log. Okay, now on the other hand, and also 1 minus natural log of x minus 1 cannot be 0. So first, x has to be strictly greater than 1. And second, natural log of x minus 1 cannot be 1. So x minus 1 cannot be e to the 1 or e. So x cannot be e plus 1. So on the number line, it has to be greater than 1, but cannot be e plus 1. Okay, so in interval notation, it will be from 1 to e plus 1 union e plus 1 to infinity. Okay, I somehow think I worked really hard for this question. Let me see if I get the right answer at the back of the book. It's an odd number, so let me check. Because if I make any mistake, then I rather find out also. It's not something I'm supposed to hide. Number 31.
It seems you got it right.
Oh yeah, well, surprise.
Yeah, I had been working on it for like the last 10 minutes and I'm like, I think I got it right. And it looks like I did. Just I actually messed up in one part, but besides that, it seems like I kind of got it right.
Okay, good. Oh, I get a message coming in asking, is there an answer key for quiz 1 too? I just posted. I really thought that I posted already, but our friend asked that question, and then I realized I didn't post it. But I just posted. So you go back to that quiz 1 too. You go back to that quiz 1 too, and on the top you will see the solution part. Okay, do you see that? Okay. Yeah, you can download it if you want. You can check it, and after that, if you still have questions, please let me know. Oh, you know what? You know what? I think yes. You know what? I need to add you one more point because I forgot that I have this though. I forgot that I have this. I need to add all of you one more point. If you, and as I remember, all of you actually turn in one single file, right? Instead of 2 pages, 2 files, you turn it in one single file. So yes, all of you will get another 1 extra point. Remind me if there's no change in your grade later on. Okay. Remind me. I think during the break I should be able to do it. Let me go back to our notes.
I had a question about a problem that you did for the 7.1 lecture, Thomas.
Okay.
Give me 1 second. So
you asked for 1 second, but it's already more than 1 second.
I know. So you don't have to go through the whole thing because it is a very, very long proof, but it was number 50 for 7.1.
50, 7.1, let me check.
And I just want to check my understanding of how
so we didn't do that problem yet last time, huh?
No, I don't think so. I think you just did it as an example for your lecture. And
but not number 50. Yeah, I didn't do number 50 from 7.1.
Correct.
Okay, let's do that now. Why not?
Okay, and it's just your videos are great, but I feel like I can't obviously ask you questions during the video, so it's kind of frustrating sometimes.
Here's the thing. So this is what I want you to do. So when you watch that and you have questions, okay, note what minute you have question, and then you can send me an email. Feel free to send me an email, Thomas. I watched that lesson number what, on minute number what you say this, but I don't get it. Why? Can you help me? If I cannot answer it to you by email, like I email you my explanation and you still don't get it, then feel free to ask me here.
Okay, thank you, Thomas.
Okay? Yeah, that's what question and answer for. You see, I said that before to your friend in class, to Jonathan. I think I said that when I did the lecture last semester, those videos from last semester, right? I did the lecture and I don't have enough time to do more problems, so I kept on feeling being rushed when I went over that. So instead of going over the same pain again this semester, so I used the videos from last semester for you to watch. And I believe that there are more things that you can understand compared to things that you don't understand by watching those. So even though, yes, I do expect that there could be, you may have some questions from there, but it is better than if I go over that in class first time, you have more things to catch up. So yes, feel free to let me know which one and write down which minute so that I can watch that lecture again and then go over with you. Now, please keep in mind, there were times, as I remember, I make mistakes and nobody got that until much later. Nobody got that until much later. I was like, I think I did that question wrong.
Oh no.
Yeah, it is possible what you thought you didn't understand actually came from my mistake. Okay. So
I mean, that's completely fine, but would you happen to know of like the mistakes themselves? Like
I don't remember anymore.
Okay.
I don't remember anymore. But the thing is, like, I didn't correct that right away for that part was because I actually make miscomputation instead of technical mistake. So for example, it's supposed to be 2 times 3, but I happen to write 5.
Oh yeah, I've caught a couple of those, right?
Yeah. So if you see this kind of mistake, I don't fix it because what? Hey, you know what? You can fix it yourself and just carry that. You fix that to be 6, and then you bring that 6 for whatever next steps where you use that 6 again. So that's why I don't really fix it. But there is one time I remember last semester that I get wrong answer, and then I fix that in the next meeting. Last semester, there were 2 cases. First one, I make a mistake, and then I caught that in the next meeting. There's another one problem that I get stuck during class. Then I told them I will do it at home, and then I bring it back the next meeting. So I try to be honest with you too. There are times that I get stuck myself. you know. Okay, number 50. Prove that for even power of sine, integral from 0 to pi over 2 of sine to the 2n x dx is equal to 1 times 3 times 5 all the way to 2n minus 1 over 2 times 4 times 6 all the way to 2n times pi over 2. Okay, I will use the problem from number 49. Hold on, I have chat coming in. This problem might have been the hardest to understand from this section in terms of dissecting it. I agree with you. I prefer to start this problem from number 49. Okay, so it's actually continuation from number 49. Number 49 says this, from 0 to pi over 2 of sine n to the n of x dx is equal to n minus 1 over n integral from 0 to pi over 2 sine n minus 2 dx. Now, suppose we will use this. We'll prove this later on, okay? But suppose this is true. Suppose number 49A is true. Then going to number 50, integral from 0 to pi over 2 of sine to the 2n of x dx. Basically, I change this to the power of n, change it to the power of 2n. What do you think? Then all the n becomes 2n. Is it right? All the n becomes 2n. Agree? Okay, on the right hand side, then it becomes integral, I'm sorry, 2n minus 1 over 2n integral from 0 to pi over 2 sine 2n minus 2 of x dx. Okay, now I will keep on doing that. I will keep on doing that. So if I use that again, but this time this is to the power of this. If this is our n, then it will be 2n minus 2 minus 1 over 2n minus 2 integral from 0 to pi over 2 sine to the 2n minus 4x dx. Can you follow me? So I replace the n here by 2n minus 2. 2n minus 2 minus 1, 2n minus 2, that's 2n minus 2 minus 2.
And then how did you get the 2n minus 4?
Because whatever I have here, I subtract that by 2 here. So whatever I have here, it's 2n minus 2 minus 2.
Okay, I think I understand.
Okay, now then the thing is we will keep on doing that. We will keep on doing that. So we have 2n minus 1 over 2n times 2n minus 3 over 2n minus 2 all the way until you have 3 over 4 integral from 0 to pi over 2 of sine squared x dx. Is it okay so far?
Yes.
Now then, when we compute that later on, you will get 1/2 times pi over 2. Okay. Let me do it then. Let me do that. Or maybe I do it separately first. So I want to compute found integral from 0 to pi over 2 of sine squared x dx. But this is, how should we do this problem? This is 1 minus cosine 2x over 2 dx. That's 1/2. Integral of 1 is x. Integral of negative cosine is negative sine. Okay, and then there will be 1/2 times pi over 2 minus 0 minus 0 minus 0. So basically 1/2 times pi over 2, which I purposely don't multiply because I want to copy paste that there. Now the thing is, if you rearrange these factors, I will write the 1/2 first. 1/2, I write that first. And then the 3/4. And then the one before that will be 5/6, all the way to 2n minus 1 over 2n times pi over 2. Now then numerator with numerator 1, 3, 5, all the way to 2n minus 1. At the bottom we have 2, 4, 6, up to 2n times pi over 2.
Okay. So in
Does
the
it make
video,
sense right now?
I'm sorry.
Repeat again.
Would this problem be done right here?
Yes, huh? Yeah. I don't think I did this problem in the video.
Oh, you did for
I did?
yeah, for 4A, I believe.
Number 4A, you mean 49A?
Oh no, for week 4A, the first video for this week.
Oh, I see.
But the way you did it now compared to the way you did it before, the way you did it in that video was very hard to understand.
Oh,
This one is
yeah.
much easier compared to.
Oh, I see. Now, at that time, did I use number 49 or I just
You did
jumped
not
right
use
away?
49 as a reference.
I think that's the reason. Yeah, I think that's the reason. Yeah,
Okay.
I did. Yeah, I think that's the reason. So if you try to do number 50 standalone without utilizing number 49, then you will do a bunch of integration by parts.
It was really rough.
Yes, yes, I understand you.
Yeah.
Yeah, so that's why I use number 49 here.
Okay.
Okay, and good that you asked it. So what I did in that video, I believe, was that I tried to do number 50 by repeatedly you doing number 49 idea.
Oh, so it's pretty much two problems in one, kind of.
That's right. I combined them right away. Maybe at that time I didn't see that. I didn't see number 49. I just jumped to number 50 right away. That could be the case. Yeah. Okay, that's for this question here. And actually, according to my plan, that's what I want to do for this 7.1b. Let's do one more questions or two more questions that has that reduction formula. Let's say, for example, number 54. That is so fun.
Are you being for reals or are you being sarcastic?
I think that was quote unquote fun. No, I mean, I look at the reason I picked that question is because it looks so scary. But you rather me do scary problem in class instead of Mickey Mouse and then you do the scary one at home, right? Okay. No, it's not fun for me. No, trust me, when I say it's fun, it's like really, yeah, sarcastic even to myself. Okay. No, I picked this question because it seems scary. Yeah, but I don't stand back simply because I see someone scary. Simply because I see that person is big doesn't make me walk away from that person. I don't really tell that kind of story anymore in class. But I did tell that story, those kind of stories when I was in pre-algebra. When I taught pre-algebra, I told a lot of stories like that. My hoodlum days, hoodlum days. Not really. You know what? Let me turn off the recording. Pause. Proof. I will rewrite this secant to the n x dx. I will rewrite that as secant to the n minus 2 of x times secant squared x dx. And then I do integration by parts. The derivative of secant is n minus 2 times secant n minus 4 of x times derivative of secant is secant tangent times secant tangent, secant x tangent x. While on the right hand side, the integral of secant squared is tangent, right? Okay, so according to our integration by parts, this will be tangent x times secant to the n minus 2x minus integral of n minus 2 secant n minus 3x times tangent squared x dx. Is it okay? But then n minus, I write n minus 3 because I multiply this. That's how I get the secant to the n minus 3. Is it okay? Now, then.
Sorry, how did you get the tangent squared x? You have one tangent there.
Tangent. Oh, because the first term here coming from the diagonal.
Right.
The one with integral is horizontal. But I have tangent here. Times another tangent, I get tangent squared.
I thought using the tabular method, you always go diagonal.
No, not always. Not
Okay.
always. Yeah. In fact, that's even true even in my last question and answer. Mm-hmm. That sometimes we have to flip that. Remember, I said that sometimes we need to flip that, right? So we need to do diagonally, and here we need to flip that. Okay, and we will see that better when I rewrite that tangent squared in terms of secant squared minus 1. So let me do that first. That's n minus 2. Let me factor this out, and then integral secant n minus 3x times, I rewrite secant squared, tangent squared as secant squared x minus 1 dx. Oh, you know what? My bad. I'm supposed to subtract only by 1 here, not by 2. So it should be 3 here. So it should be, now becomes 2 here. Becomes 2 here. See the exponent n minus 2, when I subtract by 1, it becomes n minus 3, right? So not minus 4, minus 3. Then I distribute that. So I have tangent x secant x minus 2 of x minus n minus 2 integral of, it becomes 2 terms, secant to the n of x minus secant to the n minus 2 of x dx. Now I will distribute my n minus 2. Hold on, the left hand side is secant to the n, right? Integral secant to the n of x dx. Let's call that I. Okay, so here I will have n minus 1 in n minus 2 integral secant to the n of x dx plus n minus 2. It becomes plus because of this negative times this negative here. Okay. Of integral secant to the n minus 2x dx. Now the next line, I rewrite that integral secant to the n x becomes I, so the right hand side becomes tangent x secant n minus 2 of x minus n minus 2 times I plus n minus 2 times integral of secant to the n minus 2x dx. Is it okay? Now then I will add n minus 2 to both sides. So I get n minus 2I to both sides. So the right hand side becomes tangent x secant to the n minus 1x plus n minus 2 times integral secant to the n minus 2 of x dx. Now, when I combine like terms on the left hand side, I get n minus 1 times I. Now the last step will give us what we need. We divide by n minus 1. So the I will be tangent x secant to the n minus 2x over n minus 1 plus n minus 2 over n minus 1 times integral of secant to the n minus 2x dx. Okay, now remember our I first secant to the n of x dx. That's the end of the proof. Now, it doesn't give us a full solution, but at least the situation is getting better. Why? Originally, we have the secant to the n. Now, the integral becomes secant to the n minus 2. So, how to say that? That's 2 degrees lower. Okay, so if you have secant to the 4, you basically do it twice. Okay, if you have secant to the 4. If you have secant to the 6, then you do it 3 times. But you already have the formula. So for n minus 2, you basically replicate what we did here, but instead of using n, you will use n minus 2. Okay, that's why they call this power reduction formula, because instead of getting the explicit solution, we reduce to integral of lower power. Okay, now let's see more questions, but the ones that I'm about to do right now is more about what we learned in Calculus 1. There's a chance that what we learned in Calculus 1 was not enough. That's why I want to go over this again. For example, number 62, we have y equals to e to the x, and y equals to e to the negative x equals to 1. Okay, the question is find the volume generated by rotating the region given by the curve. So what we have is e to the x, that's what it looks like. E to the negative x, this is what it looks like. And x equals to 1. So basically this region here. basically that region. Now then, what we want to do is revolve that about y-axis and find the volume of the revolved region. So if I revolve this and revolve this, I get something like this. Okay, I get something like that. Then find the volume. Find the volume. The volume will be equals to integral from 0 to 1, right? Because x will move from 0 to 1. Okay, and then it's to find the volume, let me get one band there, one strip. And this is the strip that I will revolve later on to get the shell. The radius is x, okay, multiplied by the height of the shell. So let's take a look. Okay, so this is the shell. Let's say this is the shell. Let's say this is the shell. Right? Okay. The radius here will be the distance from 0, right? Because the y-axis. So this is the radius, it's x. How about the height? The height will be e to the x minus e to the negative x. Is it right? The height of that shell will be e to the x minus e to the negative x. And then I rotate that by 2 pi. The thickness of that shell will be dx. Okay. So 2 pi times radius will give us the circumference of the base of that shell. Now, the height of that shell, okay, which if you actually flatten the shells, if you actually flatten the shell, you will see that it looks like a rectangle where the base or the length of that rectangle is the same to the circumference of that shell. And the width of that rectangle is the height of that shell. Okay, so this is 2 pi x. This is e to the x minus e to the negative x. Now, the thickness of that shell is dx. Now, the volume of this figure will be the sum of those volumes of those shells. Now, let's compute this. How do we compute this? Integration by parts, no choice, right? So it's 2 pi times the derivative of x is 1, the derivative of that 1 is 0. The integral of e to the x is e to the x. The integral of negative e to the negative x is positive e to the negative x. Integrate that again is e to the x minus e to the negative x. So, you see the tabular method, that will be 2 pi times this guy. That's x times e to the x plus e to the negative x minus 1 times e to the x minus e to the negative x from 0 to 1. So when x is 1, we will get e plus e to the negative 1 minus e minus e to the negative 1 minus, when x equals to 0, this is 0 minus 1 minus 1. Oh, that's just 0. Okay, so the volume will be 2 pi times 2 e to the negative 1. So that would be 4 pi over e. That's the formula. Okay. Now, what you really need to review from your calculus 1 is your ability to set up that integral. Okay, your ability to set up that integral. I can change the question to the following. Instead of revolving about y-axis, can you revolve that about x equals to 1? So the shape later on will be something like this instead. Like that. But no, I'm not doing that kind of crazy things. No, it's not crazy. I should not say it's crazy. It's just like, why do I want to do it that way, right? Okay, as long as you can set up the basic integral, it's good enough. Okay, that's me though. That's me. Okay. If you can't even set up the integral with the basic idea, with the basic situation around y-axis, for example, then what's the point of asking you to do something that I know you can do? But on the other hand, if you know how to set it up, then set that case up when you revolve around x equals to 1 will just be a little extra work from there. Okay, but not a lot of extra work. Okay, now that's for 7.1. Let's go on to 7.2. Let me do it here. 7.2. Let me ask you to pick 10 questions from there. You choose questions. Uh, 7.2, we relies on these facts. 7.2 relies on three types. The first one, the first group is when you are doing integration with sine and cosine. Of course, we know that sine squared x plus cosine squared x equals to 1. And then the derivative of sine x is, respect to x, is cosine x. Derivative of cosine x respect to x is negative sine x. Okay, number 15. I believe that's still with sine and cosine. Okay, so that's what I call group 1. Okay, with sine and cosine, how they interact. Number 15. Integral of cosine to the 5th of alpha over square root of sine alpha d alpha. I don't know how to integrate sine alpha, so what should I do? My problem is sine alpha inside the square root. That's the ugly part. Because that's ugly, they substitute. Okay. Then du equals to cosine alpha d alpha. Okay, now before I go on, let me rewrite it this way first. This is cosine to the 4th alpha times cosine alpha d alpha over square root of sine alpha. Right? But then cosine to the 4th alpha is equals to cosine squared alpha being squared, which is 1 minus sine squared alpha being squared. Right? So later on, I will substitute this cosine to the 4th alpha by this. Okay, this guy will be my du. Okay, and this is my regular substitution u. Okay, now remember, once you change your variable of integration to u, you should not have alpha anymore there. So cosine to the fourth alpha will be 1 minus u squared being squared. Cosine alpha d alpha is du over square root of u. Once you use variable of integration u, you don't use alpha anymore. Not supposed to, not supposed to. I know some instructors say, okay, I tend to say, okay, I don't have issue with that. But then once you have x or alpha and u being mixed up into an integration, then you wonder if that alpha should be considered a constant or a function of u. That kind of confusion arises a lot more in Calculus 3. So from now on, you learn to clear up your integration. Once you go to u, you don't use, put it this way, once you substitute that guy, don't look back. You already say that guy is ugly, right? That's why you substitute him. Don't look back, don't use that alpha anymore, okay? But once it is in this form, you see that it's actually a lot easier to work with. Why? Because all I need to do is I FOIL the top, 1 minus 2u squared plus u to the fourth du. This is u to the power of negative 1/2 minus 2u to the 3/2 plus u to the 7/2 du. And continue here. So the integral of that will be u to the power of 1/2 times 2 minus I will 4 over 5 u to the power of 5/2, and then plus 2 over 9 u to the power of 9/2 plus constant. Now I change that u back to the sign. So 2 times square root of sine alpha minus 4 over 5 sine squared alpha square root of sine alpha plus 2 over 9 sine to the fourth alpha square root of sine alpha plus constant. Okay, in between I actually did this. For example, u to the power of 5/2, that's actually u squared times u to the power of 1/2, right? U to the power of 9/2, that's u to the 4 times u to the 1/2. That's how I actually simplify that sign faster. That's for number 15. Any else?
How did you get the, or I think oh, never mind. I think I understand how you got the square, the radical. What you did was you converted the 9/2 to u to the fourth, or
yeah,
the
u to the 4
5/2.
times, yeah.
Right. Okay, got
u
it.
to the 4 times u to the 1/2. Then I change that u back to sine alpha.
1/2.
Right?
Got it. And then that u to the 1/2 is a sine, radical sign. Got it.
That's right. That's for number 15. That's how the sine and cosine interact. The second group, while waiting for you to bring up more questions, the second group is the group that have interaction between tangent and secant. Tangent x plus 1 equals to secant squared x. And the derivative of tangent x respect to x is secant squared x. However, the derivative of secant x respect to x is secant tangent. Okay, but there's one special integral that you need to memorize here. First note is integral of secant x dx. This is equal to tangent x plus secant x plus constant. No, that's not really true. Natural log of this. Move this a little bit to the right. And it should be natural log of absolute of tangent plus secant plus with that constant. Okay, also integral of tangent x dx is equal to natural log of secant x plus constant, which we can also write. Let me show you how it works for tangent x proof for the last one. That's integral sine over cosine dx, right? Okay, then I changed my u cosine x to be my u, so my du will be negative sine x dx. You should just memorize. You don't need to memorize the proof. No, you don't need to memorize the proof. Even though I think you should be able to reproduce the proof without memorizing it. This one is quite simple such that I don't think you need to memorize it. You just need to see it once. Yeah. Okay, so then this integral becomes integral of negative du over u, which is negative natural log of absolute u plus constant, which is supposed to give us negative natural log of cosine x plus constant. Now the thing is, why it becomes secant, Thomas? Because of the following. We can rewrite that negative as negative exponent to the power of -1. Remember that? But the reciprocal of cosine is secant. So you can say that the integral of tangent can first be seen as negative natural log of absolute cosine, which simplifies to be like this. Okay, now another one that you need to memorize. You don't need to memorize the proof. It will be nice if you see how the proof being done. Is integral of secant cube x dx, which I somehow believe I went over that in my lecture. Okay, which is equals to 1/2 secant x plus tangent x plus 1/2 natural log of secant x plus tangent x. Don't forget plus the formality plus constant. Now the proof is actually in the book. Okay, example 8. Example 8. You can try to do that though. If I were you, you should try to do that on your own. Okay, you see the proof and then say, oh, you know what? Let me try to replicate what they did. Okay, it involves integration by parts somewhere in between. Okay, but I told you to memorize this because we see some questions that becomes very difficult if you don't know this fact. Okay, if you memorize, that would be great. Okay, any problem you want me to do either from group 1 or group 2? That involving sine cosine or secant tangent. I know, yeah, secant tangent. Nothing? Don't surprise me. Now, worse in worse, if you can't do, like you don't know how to, let's say, for example, if we have cotangent and sine, what do you do? Okay, we don't have that in any group, right? Cotangent and sine, then change them into sine cosine. Okay, change them to sine cosine. There are many ways to approach that problem though. If you don't choose any questions, let me do randomly choose one of them. Let's say number, which one's good? Number 28 maybe. Integral of tangent to the fifth of x times secant cube of x dx. The reason I told you this, the derivative, okay, we have secant tangent, okay, because then if my secant and tangent are both odd, then I can pull one tangent and one secant away. And use u equals to secant instead, secant x, such that du is tangent x secant x dx. And then the integral becomes, let me continue here, the integral becomes tangent to the fourth equals to tangent squared being squared. But tangent squared is secant squared x minus 1, that's tangent squared, being squared. Okay, in terms of u, this will be u squared minus 1 being squared. Okay, so this becomes u squared minus 1 being squared times secant x, secant squared x becomes u squared, times tangent x secant x dx, that's du. See, that's polynomial, right? So that's integral of u to the 6th minus 2u to the 4th plus u squared du, and the integral becomes 1 over 7u to the 7th minus 2/5 u to the 5th plus 1/3 u cubed plus constant. And then I fix it up, becomes 1 over 7 secant to the 7x minus 2/5 secant to the 5th x plus 1/3 secant to the cube, secant cube x plus constant. The challenge is really, how do you know what to do in what situation? Somehow I think number 32 may be hard, but it could be very easy. How about cosecant and cotangent terms? You can see that as group number 3. Group number 3, how the cosecant and cotangent interact. The facts that you need to know is 1 plus cotangent squared x is cosecant squared x. The derivative of cotangent x respect to x, as I remember, is negative cosecant squared x. That's what I remember. I need to show the work for myself. Is it right? Let me check first. Let me check. The derivative of cosine x over sine x, the derivative will be, I have sine squared x at the bottom, negative sine x times sine x minus cosine x. That's negative 1 over sine squared x. Yeah, that's right. So the derivative of cotangent x is negative cosecant squared x. the derivative of cosecant x respect to x is negative cotangent x cosecant x. What else that we need to know? From group 3. I don't know, I don't remember. Then how do we do question like number 40 times? Question number 40, integral from pi over 6 to pi over 3 of cosecant cube x dx. Honestly, I don't know. Honestly, I don't know. But let me try. This is equals to integral pi over 6 to pi over 3 of cosecant x times cosecant squared x, which is 1 plus cotangent squared x dx. I wonder if that helps. Oh, no, not a good idea. No. Just keep it as cosecant squared. Because the derivative of, then I do integration by parts here. Okay, the derivative of cosecant x is negative cotangent x cosecant x, yet the integral of cosecant squared x is negative cotangent x. So by integration by parts, this becomes negative cotangent x cosecant x from pi over 6 to pi over 3 minus the horizontal product. So I have integral sign in front of that. Integral, 2 negative becomes positive. And I have cosecant x times cotangent squared x dx with limits of integration from pi over 6 to pi over 3. I will compute that later on. Okay, now then, the integral on the right hand side here, I will rewrite that into cosecant x times cosecant squared x minus 1 dx. And rewrite cosecant cube x dx plus integral of cosecant x dx. Now the thing is, this guy on the left hand side is the same to this guy on the right hand side. Okay, so if I add both sides by those integrals, I will get 2 integral from pi over 6 to pi over 3 of cosecant cube x dx equals to negative cotangent x cosecant x from pi over 6 to pi over 3 plus integral from pi over 6 to pi over 3 of cosecant x dx.
I have a quick question, Thomas.
Uh-huh.
2 steps before, you had a cosecant squared x minus 1 in parentheses.
Uh-huh.
How did you get rid of that minus 1? Like, what did you?
No, I didn't get rid of that. Imagine if I distribute that.
Okay.
So inside here, it becomes cosecant cube x minus cosecant x, right? But I have negative outside.
Oh, so you just applied it.
Yeah, so I apply this, I distribute this negative toward this and separate them.
Gotcha. Okay.
So I get this one and then I get this.
Thank you.
Okay, now then finally I divide by 2. I'm not really done yet. I'm not really done yet. Cosecant x from pi over 6 to pi over 3. For that part is just computation of this, right? So the hard part is on the right hand side. What is the integral of cosecant x? What is the integral of cosecant x? As I remember, that will be natural log of cotangent x minus cosecant x. I might be wrong. But let me check. Instead of attacking it directly, let me do the derivative of this ugly guy. So natural log of cotangent x minus cosecant x. If I do the derivative, what do I get? That will be 1 over cotangent x minus cosecant x times the derivative of cotangent x is cosecant squared x. The derivative of cosecant x is cosecant cotangent. Is it right? What is the derivative of cosecant? It's negative, so it becomes positive. The derivative, so I have another negative here. And then I will factor this negative out, so I get, I factor negative cosecant x out. So I get cosecant x minus cotangent x. Oh, okay. So this is the opposite of this. Cancel that negative. So the derivative is cosecant x. That implies, okay, so that implies integral of cosecant x dx is that natural log of cotangent minus cosecant. Okay. Now then, plug in numbers. That's negative 1/2 times, what is cotangent pi over 3? 1 over radical 3. What is cosecant pi over 3? That's radical 3 over 2. So 2 over radical 3. That's the reciprocal of sine, right? Minus cotangent of pi over 6. That's radical 3. Sine pi over 6 is 1/2, reciprocal is 2. Plus 1/2 times natural log of cotangent pi over 3 is 1 over radical 3 minus 2 over radical 3 minus natural log of I know it looks ugly. So negative 1/2 times 2 over 3 minus 2 radical 3. That will be radical 3 over, that's radical 3, oh, that would be radical 3 minus 1/3. That's for the first group, plus this is 1/2. Inside I get natural log of 1 over radical 3 minus natural log of radical 3 minus 2. Is there any way for me to simplify that? I don't really have that. So that's natural log of the quotient 1 over radical 3 times radical 3 minus 2. So radical 3 minus 1/3 plus, actually minus 1/2 natural log of 3 minus 2 radical 3. That's what I get. Unless I make miscomputation. I know when I did the integral is okay, but when I plug in numbers, I may make not a good mistake, not a good thing. I may make mistake somewhere. Okay. Things that you need to be aware. I skip one little step when I combine these two to be like this. Okay. So that's for that question. What question is that? That's number 40. Now, there's one formula that you need to, one group of formula you need to memorize. That's a product to sum formula. Product to sum from your trigonometry class. Okay, that's basically cosine A times cosine B equals to what? That's 1/2 of cosine sum plus cosine difference. And then sine A sine B becomes negative 1/2 of cosine sum minus cosine difference. And then sine A cosine B is 1/2 of sine sum plus sine difference. It's in the book right above the exercise set. Okay, so if you need to look at the book, at least you know where to get it. Okay, that answers question like number 42, which without that that formula, you won't be able to do at all. But once you apply that formula, it becomes Mickey Mouse. That's equal to integral of 1/2 cosine sum plus cosine difference. Okay, so that's 1/2 times 1 over 5 pi sine 5 pi x plus 1/2 1 over 3 pi sine 3 pi x. Don't forget plus constant. Well, by the way, I use one little known. No, that's a lot of you supposed to know that. Cosine negative is the same to cosine positive. Cosine negative x equals to cosine x because cosine is an even function. Okay, that's why the integral of that cosine 3 pi x give me that 1/3 3 pi sine something.
Wait, sorry, could you explain that one more time, Thomas?
Cosine negative angle, cosine negative theta equals to cosine theta. Sine negative theta is negative sine theta. Sine and tangent are odd functions.
Oh, right.
Cosine is even function. Okay, so the last step will be fixing them up. Sine 5 pi x over 10 pi plus sine 3 pi x over 6 pi plus constant. Oh, number 46 and 48 are actually on the difficult side. Maybe. I don't know. I look at that, I have no idea. Number 46, but I think it has something to do with double angle. I think it has something to do with double angle formula. So 1 minus cosine for theta d theta. Now we know the following, that cosine, or actually sine squared theta is equals to 1 minus cosine 2 theta over 2, right? Okay, so 2 sine squared theta is equals to 1 minus cosine 2 theta. Is it right? So if I replace the theta becomes 2 theta, then the theta becomes 2 theta. Is it right? Now then, this integral becomes integral from 0 to pi over 4 square root of 2 times sine squared of 2 theta d theta. The square root of 2 goes all the way out. And then square root of sine squared 2 theta is absolute of sine 2 theta d theta. Now, the thing is, the domain of integration from 0 to pi over 2 will give sine 2 theta always positive anyway, such that I don't need to worry about that square root. I can take it off. Okay. A little explanation is as the following. In this interval 0 to pi over 4, sine 2 theta is non-negative, right? So absolute of sine 2 theta in that interval can be rewritten as sine 2 theta only. Okay, now then the integral of that will be 1/2 square root of 2 times 1/2 negative cosine 2 theta from 0 to pi over 4. So that's radical 2 over 2. Okay, 1 minus 0. That's, oh, the answer is radical 2 over 2. The one that I have no clue is number 46. Honestly, I look at that, I have no idea.
Wait, didn't we just do 46? Or are you talking about 48?
Oh, 48.
Okay.
Thank you. Yeah, 48, 48. 48. I have no idea, but I guess I will multiply by the conjugate. So on the bottom, I multiply by cosine x plus 1. So on the top, I will get cosine x plus 1 dx. Wish me luck. So this becomes integral of cosine x plus 1 over cosine squared minus 1, that's negative sine squared, dx. This is actually not bad. This is negative integral of cotangent x plus cosecant x dx. Nice. So what is the integral of cotangent? What is the integral of cosecant? You figure out. I think the integral of cotangent is, let me guess, that's natural log of something. That's negative of, that's natural log of sine cosecant. Right? Integral of cosine x over sine x dx. Oh no, actually just sine. Okay, this is equals to, if this is my u, then this is my du. That's natural log of absolute u plus constant. Okay, but how about the integral of secant x? The integral of secant x is negative or plus, plus natural log of cotangent x minus cosecant x. Of course, plus constant at the end. Wait, this is actually a nice one. This is negative natural log of cosine x minus 1. Huh? How do you get the times? Well, because sine x times cotangent x gave us cosine. Cosecant x multiplied by cosecant x, that's 1. That's way too nice. I didn't expect that answer though. I wonder if I make any mistake. See, the reason I get this, the reason I get the last step here, that thing here, is because the sum of log equals to log of product, right? So that's actually becomes natural log of this. Does it make sense? But then inside it simplifies to be cosine x minus 1 only. I wonder if I get the right answer there. It's way too. I question myself. Your suggested homework from here, I believe you see that in my lecture. Let me give myself a little break. I need some break. We come back at 9:25. Of course, I cannot finish this 7.3 today, but at least I give you the starting point and idea. This is on inverse trig on trigonometric substitution. Seven point three on trig substitution. Idea. We want to tackle or take care the substitution that is needed to get rid of radical something. For example, square root of 1 minus x squared. What is the substitution we can use for x such that the whole radical 1 minus x squared becomes a nice expression? And what we can use is we let x to be sine theta. Okay, now if x is sine theta, then this square root of 1 minus x squared will become square root of 1 minus sine squared theta, which becomes square root of the cosine squared theta, which becomes absolute of cosine theta. Okay, so if you have square root of 1 minus x squared, that's what you do. The variation to this is what happens if you have square root of a squared minus x squared. Then we let our x to be a sine theta. Now the purpose of that coefficient a at the front is such that when I substitute that in, I will get a squared minus a squared sine squared theta. Okay, so that we can factor the a squared, right? Minus sine squared theta, and that's a times absolute cosine theta. Okay, but the reason it becomes like this, the reason that we use this as our substitution actually coming from here. Now, what happened if instead of 1 minus x squared, we have 1 plus x squared? And think of like what our x supposed to be such that when we square it, it will combine with 1 and give us a nice function. And it is substituted by tangent theta, such that the square root of 1 plus tangent squared theta this guy becomes square root of 1 plus tangent squared theta. That's square root of secant squared theta. That's absolute of secant theta. And the variation is what if instead of 1, we have other constant. Whatever constant it is, we see that as a squared. Okay, so the substitution will be x equals to a tangent theta. Okay, so that you will see they combine nicely, becomes a squared plus a squared tangent squared theta square root of a squared times 1 plus tangent squared theta, right? Square root of a squared is a, and that becomes secant squared absolute of secant theta. Okay. Now the third case is when you have x squared minus 1. So what do we substitute that x by such that x squared minus 1 later on becomes a nice something square. And we substitute x by secant theta. Because secant squared theta minus 1 is tangent squared theta. And the square root of that is tangent theta. Now, the variation, what if we have square root of x squared minus a squared? Then we let our x to be a secant theta. Okay, therefore, square root of x squared minus a squared becomes square root of a squared secant squared theta minus a squared. I factor the a squared. The square root of a squared is a, and secant squared minus 1 is tangent squared under square root is becomes absolute tangent theta. Now, in the actual integration later on, we're supposed to change that theta back in terms to x. Okay, but we will do that later though. We'll do that later. Let's do problem first. Number 6. Number 6, integral from 0 to 3 of x over square root of 36 minus x squared dx. And actually, try to think simple. Okay, like for this one question here, we can do this by substitution. Is it right? Okay, we can do this by a regular substitution. So method number 1, let u equals to 36 minus x squared. Why? Because the derivative of u is negative 2x dx, which we have at the top, right? Without that x, we cannot do this trick. With that extra x on the top, it enables us to use this method. So we now get integral 36 and minus 9, that's 27 here. This is negative du over 2, that's for x dx, and this is 1 over u to the power of 1/2. So this is equal to integral, I absorb the negative, so I pull the 1/2 out, the negative absorbed into the reversing order of integration, u to the power of negative 1/2 du. That's u to the power of 1/2 from 27 to 36.
Quick, Thomas?
Yes.
For the negative du over 2, wasn't it negative du over 2x?
No, because x dx is this.
Oh, the x is already there. Oh,
yeah, right. Yeah. So then this becomes square root of 36 is 6 minus square root of 27. That's 3 radical 3. Okay, but that's method number 1 where I did not use trigonometric substitution at all. Now, method number 2, I will let u equals to, let x equals to 6 sine x, sine theta, don't use sine x, such that dx equals to 6 cosine theta d theta. Where did the 1/2 go? The integral of this is this. Maybe to be more precise, the integral of u to the negative 1/2 is 2 times u to the 2 to the power of 1/2, which cancels the 1/2. Okay, integral of u to the negative 1/2 du is 2 u to the power of 1/2. Okay, plus constant, of course. Now, on the second method, then we get the integral when x is 0, theta is 0. When x is 3, sine theta is 1/2. So theta is pi over 6. Notice that once I do substitution, my dx now becomes 6 cosine theta d theta. In other words, my variable of integration is now theta. Then the boundary has to be in theta right away. Right away. Don't wait. Okay, I will try to substitute that back later on, Thomas. Why? You already substitute. Don't look back. Okay, that guy is ugly. You substitute him already. Why do you want to look back? Okay, don't look back. You already changed it. Okay, now x is then 6 sine theta on the top. At the bottom, square root of 36 minus x. Let's see, 36 minus 36 sine squared theta is square root of 36 times square root of cosine squared theta, right? So that's 6 cosine theta. Supposed to be inside absolute sign. Supposed to be in an absolute sign. But because in this interval, the first quadrant, basically, cosine is positive. That's why I don't use absolute sign. Okay, and then 6 cosine theta cancels. So I get 6 integral from 0 to pi over 6 of sine theta d theta. The integral is negative cosine theta from 0 to pi over 6. That would be 1 minus cosine pi over 6 is radical 3 over 2. Okay, so for this question, we happen to be able to do it with both ways. Number 8, however, I don't think so. Number 8, however, I don't think so. Because we don't have extra t for my t squared minus 16. However, our issue is more about what happened to this guy. I want to simplify this into only one term instead of 2 terms. So let's do that substitution. Let t equals to 4 secant theta, such that dt equals to 4 tangent squared theta d theta. And t squared minus 16 becomes 4 squared secant squared theta minus 16. That's 16 times secant squared theta minus 1, which is 16 tangent squared theta, such that square root of t squared minus 16 becomes 4 absolute of tangent theta. with that setup, I'm ready to do, this is equals to integral of, what is my dt? 4 tangent squared theta d theta over t squared, that's 16 secant squared theta. Square root of t squared minus 16 is 4 tangent theta. I take off the absolute sign. Okay, so this simplifies to be 1 over 16 integral of, what will this be? Tangent on the top, but we also have cosine squared on the top. You know what? I know I can simplify this a lot further. It will be cosine theta sine theta d theta. Let's see. Let me do it aside here. Tangent squared theta over secant squared theta tangent theta. One of the tangent cancel, right? And secant squared theta, if I bring it to the top, it will become cosine squared theta, right? That's cosine squared theta times sine theta over cosine theta. The bump, the boom, that's cosine theta sine theta. Then from there, I hope you can just do, I do substitution further then. Let me do substitution further. So let u equals to sine theta. So du equals to cosine theta d theta. So now I get this is 1 over 16 integral of u du. That's 1 over 32 u squared first constant. But my u squared is sine squared theta. How about my sine squared theta? Notice that t equals to 4 secant theta. So t over 4 equals to secant theta in our right triangle. If this is theta, then t over 4 will be t here, 4 here. Now think about this. Secant theta in a right triangle. So then the opposite will be square root of t squared minus 4. Now sine theta will be square root of t squared minus 4 over 4 being squared plus c. So that's square root of, actually the square root disappears because you square it, you get t squared minus 4 over 512 plus. You need to be very patient with your integration. Don't skip steps. Okay, if you don't organize your work, you will have hard time to look back later on. Okay, there's no way for you to check your work and find your mistake if you don't have that patience in yourself. You need to be patient. Okay, that's for number 8. On Monday, then I will continue on. So on this Monday, I will continue on 7.3 and finish up 7.4. Okay, but as far as I know, our lesson 6 already includes 7.4. Is it right? Well, anyway, we are a little bit behind schedule. We are a little bit behind schedule compared to our lessons. But keep on watching the lessons. Okay, and then don't forget to do the problems. The material for your test 1 will be up to 7.4 only, not including 7.5. Or is it including 7.5? As I remember, I don't include 7.5 in my test 1. But 7.5 basically everything put together. Okay, that's for today then.
Thank you, Thomas.